we know from calculus that the derivative is the slope of the tangent. Okay? Now there are cases when instead of finding the slope of the tangent line, you want the actual equation of the tangent line, not just the slope, the whole kit and caboodle. That's the first part of the day. It's really two totally separate ideas. Tangent line and higher order derivatives are different. So the objective is to be able to find a tangent line to a curve, the equation of the tangent. And then there's also a use of what it does, and we'll talk about how that can be used. Let's do the first part first, all right? So in this example, I have the square root function, and I want the equation of the tangent line at x equals 4. Now here's x equals 4, and okay, I guess I'll do it that way. Your goal is to find that black line. Do I have that on there, or you want it? I have my line wrong, but my bad. I hope you draw the line where it was, because I want the line there. You want it barely skimming at 4. You follow me? That's the tangent line, and we're trying to find its equation. Now, in Algebra 1, you definitely love that slope-intercept. It's pretty good. But in calculus, point slope is better. So, when you're going to find an equation of a tangent line, the first thing we're going to do is find a point on the curve. Well, sometimes they're going to tell you, find it at this point. So what is a point where we're going to draw the tangent line, or a point that the tangent line will run to? Well, the x is 4 because that's where they said to draw the tangent. What's the y? 2, because the square root of 4 is 2. Cool? All right. That's good. That's one thing that will help us draw a tangent line. We know one point on the tangent line. Now we need the slope of the tangent line. I don't want to just try and eyeball it. I want to calculate. How do I find the slope of a tangent line? The derivative, all right? So we take the derivative. Now, be careful of notation because this needs to be done in 2 steps. First, find the derivative, then find the derivative at 4. So what is the derivative, given that as a power, we're dealing with x to the half? 1/2 x to the negative 1/2, which is equivalent to 1 over 2 root x. You with me? Now that's the derivative. Is that the derivative at 4, or is that just the derivative at any x? Any x. And therefore it's labeled correctly f prime at x. F prime at 4 would be to put 4 in 4x, and at 4, we see the slope is 1/4. Does that seem to match the picture? Yeah, positive, flattish slope. Cool. All right. Now we're going to write the tangent line in point slope form. So point slope form is y minus. y1 represents the y of the point you're going to. So what's y1 for this problem? 2. Okay, here's x1, here's y1. So y minus 2 equals, m is obviously the slope. What's our slope? 1/4. And x minus x1, is that 4 minus x or x minus 4? X minus 4. That is all she wrote. You might ask, do I have to rearrange it and solve? No, you don't. I don't care if you solve for y. Please don't. Understood? All right. Here we go then. Would you give this a try? Use those same steps as you did above to find the equation of the tangent line to cosine of x. Please do talk it over with your math and English. Looks like most people are getting there. What'd you get for the point? The point is 5 or 6 root 3 over 2. I agree. Okay? Do you agree the derivative for cosine we learned yesterday is negative sine? Okay? So the derivative, did you label that correctly? That's f prime at x. Then in the second step, f prime at pi over 6 is negative sine of pi over 6, which is negative 1/2. Did you get the slope correct? Last but not least, did you put them correctly into the equation? Shout out your equation, somebody. Y minus root 3 over 2 equals? Beautiful. Okay. All right. So far, so good. All right. Let's talk about what this might look like with the calculator. This is also good practice for tomorrow. So would you get a calculator out? Obviously, you're not going to do a tangent line tomorrow, but you will have to do a derivative, as we just talked about. And so, would you start by putting the function into F1? Go to the graphing menu and type the function in the example into F1. And what do I got there? E to the sine plus 3 tangent 5x. Oops. E to the sine of x plus 3. What does it say? Plus 3 tangent? Is that what it said? Plus 3 x 5x. Okay. Ooh, baby. That's so pretty. It looks like wallpaper. Okay. So go back to the home screen now, and same kind of idea. What are the really just 3 steps to a tangent line? Point, slope, point, slope. So how do we find the point? Yeah, we need f at 2.75. So evaluate the function at 2.75. Remind me, in my calculator, how do I evaluate a function that's already in? Go to vars to recall the function. You hit vars to get the function back, and then type in the value. Let's go with 3 decimals, so 8.822. You track it. 8.822. So my point is 2.75, 8.822. Are we cool on the point? All right, this is where you must communicate well, so pay attention here. I don't want just m equals this. You must, even when you're using your calculator to do the heavy lifting, you have to communicate what you have the calculator do. So you're having the calculator do what? Find the derivative at 2.75. So it's not enough to just start reporting. You need to say m is f prime at 2.75, and then it's understood that your calculator is making that calculation, but you need to communicate that derivative idea. So remind me again, how do I calculate the derivative at a point? Menu, calculus, derivative. X is good. 2.75, is it 75? Yeah. Okay. All right. Now, do I have to type in the whole function? No. What should I type in there? Yeah, go to vars and give it f1 of nothing, of 2.75, or x? X. We want the derivative of function 1. And I get 103.867, which normally would freak me out, but looking at that graph, it was really steep there. So it seems okay. Are we cool? Okay. 103.867. We've got a point, we've got a slope. Now what do? Point slope. So y minus 2.75? 8 point something, 8.822, yeah? Equals 103.867 x minus 2.75. All right. Are you with me so far on making a tangent line equation? You feel like you could do that with or without a calculator? Okay, cool. Now, pause for a second. If I went back to this graph here, if I looked at what's going on at 5, wouldn't the square root of 5 on the red graph and 5 in the line be almost exactly the same? Really, really close to each other? Okay. What about at 10? Are those as close to each other, or they're a little further away? A little further away, okay? Now, which would you rather work with? If I said, hey, give me a doggone good estimate, if I said put 5 in, what could you do easier? The square root of 5, or put 5 into the line equation? I mean, if I put 5 into the line equation, wouldn't it be pretty easy? It would just be 2 plus a fourth times 1. So 2 and a fourth. You with me? My point is that the line equation is really easy to work with, whereas the square root at ugly numbers, not so much. Now that's actually the biggest use of a tangent line, is at points close by to the tangent line center, the two are really close to each other. And I could use the tangent line to estimate really ugly stuff. That's the next point. That's the use of it. If I can advance the slide, that's what I did too. Okay, so if, for example, I asked you to estimate the square root of 5 in pre-algebra, I'd say, all right, kids, first try 2.1 times itself and see if that's close to 5, and then try 2.2 times itself and see if that's close to 5, and at that point it's boring, right? But this is cool. If I want to estimate the square root of 5 using my line, then we could take the line. We have the line already, was y minus 2 equals 1/4 x minus 4, yay? Is that right? Yeah, okay. Now if we evaluate that at x equal 5, then isn't y 2 plus a fourth? If I move the 2 over, then it's 2 plus a fourth times 5 minus 4, or 2 and a fourth. Now that took practically no time. And what is the square root of 5? I'm curious to see how good my estimate is. 5 is 2.236. So we're 200ths off. And that took practically no time. Now that's the idea of using a tangent line. You make the tangent line, and then you put the number you're trying to estimate into your tangent line, because lines are so easy to work with and easier than square root uglies. So next question. Is that estimate, 2 and a fourth, is that a little more or a little less than the true square root of 5? Why? Besides, I just told you what the values are. How does the picture tell you? Yeah, when I put 5 into the tangent line, I said what's the y on the line as opposed to the y on the curve. And isn't the line a little above the curve? All right. What makes a tangent line above a curve? Is a tangent line always above a curve? What kind of curves would the tangent line be below it? How about that? Would you agree the tangent line would be below there? And that goes to concavity, concave up or concave down, but for now we'll just say it is less than the true value, more than the true value. You see where I'm coming from? More because the line is above the curve. And so its y is better or bigger. All right. Now, what if we tried to use our line to estimate the square root of 6? Would we be as accurate at 5, or more accurate than we were at 5, or less? Less. Why? Because there's a bigger difference between the line and the curve here. And at 7, an even bigger difference. And 8, an even bigger difference. If we wanted to estimate the square root of 8, and we wanted to do it better, how could we do it? Yeah, instead of doing a tangent line at 4, which is way far away from 8, we could do a tangent line at 9 because it's clean, it's a good square root, and it's doggone close, and it has a smaller difference. So to get further, the idea is further from x equals 4 yields a worse estimate. And if we wanted to estimate the square root of 8, we could get a better estimate by using a tangent line at x equals 9. Be far less error. Alright? So let's do that and use it to estimate. What do we need? What 3 steps to a tangent line? A point, slope, and a point slope. Okay? So, in this case, what are we going to use for the point? 9. Now we're going to do a tangent line at an x of 9. And what's the y at 9? 3. Remember, the function is the square root function. Okay? Now we already know the derivative is 1 over 2 root x. So that's f prime at all x's. So I don't need to redo that, but I do need to recalculate what's the slope at 9, because it's certainly different than where it was at 4. So what's the derivative at 9? 1/6. So what's the tangent line equation? Y minus 3 equals 1/6 x minus 9. Now if we use that to estimate, then what do I put in? I want to estimate what the square root of 8 is. So what do I do? I put x equal 8 into the line. And y is 3, if I move it over, plus a sixth of 8 minus 9. That's 3 minus a sixth, which is 2 and 5/6. About 2.833 is a good estimate of square root of 8. Yeah? Track it. Let's try one together and then one on your own, and we're good. All right. So if I ask you to use a tangent line to estimate, then you first need a tangent line, then you estimate. So let's first get in our head, if I'm trying to estimate the natural log of 2, maybe it would help to start with, what's the function? What's the function here? Natural log of x. You could call it y, you could call it f of x. That part is not important. I think I'd rather call it f of x. Okay? Now, it says we're trying to estimate natural log of 2, and sometimes it'll tell you what point to use as your good point, but sometimes not. In this case, they're telling you use a tangent line approximation at x equal 1. That means you draw your tangent line at x equal 1. Well, why do you reckon we chose that? Yeah, log of 1 is known. Log of 1 is e to what power is 1, and that is the 0th power, right? Okay, m. How do I find m? Find the derivative generally, and then find the derivative at 1 or 0? 1, right. So yesterday we talked about the derivative of natural log. What is it? 1 over x, and therefore at 1, slope is just 1. Okay? Alright, I got the function, I found a point, I found the slope, now what do I do? Now you write the tangent line. What is the tangent line equation? Y minus 0, which surely you could just not write at all, equals 1 times x minus 1, or just y equals x minus 1 if you like. Yeah? Okay, am I done? Now we use it to approximate what happens when x equals 2. If x equals 2, then y is 1. So we would say that the natural log of 2 should be close to Not equal to, it's an approximation, but close to. You follow? All right, would you, is there not one for you to try on your own? Oh, there is? Oh, what is it? Cube root of 7. Let's make the cube root of 7. Okay. Cool, you try. Feel free to talk it over for math amigos. For the point, do I use an x of 7? No, I don't know that. I use 8. 8's a good cube root. Sears is absent again. Gosh. Your estimate is? 1 and 1 and 11 twelfths. Did you get it? Okay. If the answer is no, then let's take a look. First of all, sorry, I'm trying to do this blind, so do you agree that the point we're going to use is 8, which cube rooted is 2? Okay. Do you agree that the derivative of x to the third is 1/3 x to the negative 2/3, which is the same as 1 over 3 times the cube root of x quantity squared, or if you like, x squared then cube rooted, it's the same. That said, I have a problem here in my labeling. Where's the mistake in my labeling in the derivative part? The second step shouldn't be f prime at x, it should be f prime at a. And that is 1/12. Do you agree with the slope, 1/12? If not, figure out your mistake. Therefore, the line is y minus 2 equals 1/12 of x minus 8. The approximation part then comes when you say, well, if I put x equals 7 into the line, I get 2 plus a 12th of 7 minus 8, which is 1 and 11, 12. And did you just check the good?
Yeah, it was like 0.04 off.
Okay, so 400's off. Pretty good, all right? You can imagine how tedious it would be to approximate something times itself 3 times to get 7. That would be really gross, to the hundreds especially. All right, so it's pretty good. Higher order derivatives. So there are a lot of times where you don't just take a derivative, you take a derivative of a derivative, especially in physics, but in lots of things actually. Let's go here for the benefit, actually juniors maybe understand. When you talk change in position over time, what is that? Velocity, okay? If I want then the instantaneous rate of change in position, that's the derivative of position is velocity. Cool. But what if I would then take the derivative of velocity? What's change in velocity? It's acceleration. If I go from 30 miles per hour to 50 miles per hour, I accelerate. Increase my velocity. Now that's actually the derivative of the velocity, but it's the derivative of the derivative of position. The point then is sometimes you want to take 2 derivatives, or a second derivative, or even a third derivative. What's the third derivative? Anybody know that? Is anybody an AP? It's jerk? I can never remember. Okay, I don't do it in that stuff. All right, there's jerk, and after that there's something. Oh, I can't believe that's a thing. Great. So there are lots of derivatives after that. Physics, I think some smoking something. I don't know what they're called. It's crazy. I'll have to ask Mr. McCullers. All right. Let's start with notation real quick. If the original notation was y equals something, then the way the derivative is written is either y prime or, in Leibniz notation, dy dx. Okay, that stands for tiny change in y. It's like a tiny delta y over a tiny delta x. Remember that little triangle between 2 super close points? That's y dy dx, all right? Now the second derivative would either be y double, and that is often shorthand for what the second derivative. You might read that as y double. Or the second derivative of y is fine too. Leibniz notation, here's one of the few times where Leibniz gets a little cumbersome, but the notation is this. I know it feels like d squared y, or I wouldn't say it, I just say the second derivative. That's call it good. Okay? That's just the second derivative. Most students just say, you get that nonsense, I'm doing y double. Oh, that's fine. In function notation, the first derivative is f prime, the second derivative is f double. Would you write yourself a note here? In function notation, you use primes through maybe the third derivative. For example, f, that might be f triple. But at that point, that's good. If you want the 10th derivative, it is most definitely not, it's not that, and it's not that, and it's not, like Roman numeral or whatever. I've seen all that crazy crap. It's this. Oops, except that's the 10th derivative of the function. Okay? This is a no, that's a no, that's a no. That's the case. If you get a higher order derivative beyond a third derivative, typically you just write it with a little superscript. Okay, now then, let's talk about this. If I want the second derivative at 1, it's like an elevator. I can't get to the second floor unless I first get the first floor. So I first need to find y prime. It's going to be even more important that you label your work. Now instead of 2 things, the function and the derivative, you've got 3. The function, the derivative, and the second derivative. It can't just be all of them floating with no labels. That's not what you do. You've got to label. So the derivative is What's the derivative of 2x squared? 4x. What's the derivative of 3? 0, so I'm just going to leave that out. What's the derivative of the e to the x? And what's the derivative of log of x? Correct. Perfect. Do I need to put in 1 into that, or no? Let's say puts 1 into the second derivative. Don't even bother putting in the first. I don't care about what the first derivative is of 1. That's not the question. I do need the second derivative. So what's the derivative of 4x? 4. What's the derivative of e to the x? E to the x, and here I might at least make a mental rewrite here. Be careful. This is x to what power? Negative 1. So when the derivative comes around, what's the derivative of x to the negative 1? Negative 1 over x squared. The negative would come down, drop it by 1. That's negative x to the negative 2, which we prefer to write that way. You follow? Now, if I were to label this well, that's why double at any x or at 1? Any x. And so y double at 1 is 4 plus e to the 1 minus 1, or 3 plus e. Let's just pause and also stop something that makes me crazy. If somebody then says, oh, that's not good enough, I'm going to be an overachiever and pick up my calculator, does that take more time to put that in your calculator? Yeah. Is that answer better? No, the minute you put it up in your calculator, is it exactly? No, now you're going to be rounding. So tell me, why would you do more work for a less exact answer? That doesn't make any sense to me. So when students say, should I pick up my, no, you should not. You should call it good, because that's exact. And you're not doing better by picking up your calculator, you're doing worse. All right. Would you give this baby, let's just do it together in order to get through it sometime. Given the position is this, all right, so S represents where it is on a number line in one dimension, and T is the time, meters and seconds. Cool. Find V. Now this is important that you label. Velocity is the derivative of position. And the derivative of that position function is 8t plus 3. Now, what are the units on that? Now keep in mind here, S prime is great, but better is ds dt. Change in position. Now what are the position units in the top? Meters, and the change doesn't change that fact. It's still change in position, which is in meters. What's the time units in the bottom? Seconds. So that's in meters per second, whatever the case might be. At some time it would be different. Each time it would be different, all right? Now the acceleration could be expressed calculus-wise two different ways. I mean, two different ways to say what acceleration is. Okay, it's either the change in the velocity, or the derivative of the velocity, or the second derivative of position. Either way, I need to take the derivative of the velocity. What's the derivative of 8t? 8, and the derivative of 3? 0. And a prime is dv dt. And what are the units on velocity? Meters per second. And what are the units on time? Seconds. So you could say meters per second, or you could say meters per second squared. Now obviously a square second is bogus, but it's meters per second. Yeah? So either way is fine, but in your head, don't try and wrap your mind around a square second. Okay. All right, you follow me? Okay. So check for understanding. How do you find a tangent line? Point, slope, point, slope. When is the tangent line a good approximation? When it's close. What you're trying to estimate is close to your point of tangency. When is it a bad? Far away, especially when the curve is really curving fast and you really get a bad estimate. And what's one use of the second? Acceleration is the second derivative, among other things. Okay, cool. Homework practice. Do you have any questions on the homework? We have replacement problems we need to go over. Do I need to get this out? Oh, it's 827, 826. Let me see if I need to paste any. Oh, wow. I gave you a lot of blank space there. 21, 20. I don't know if you noticed. I'm not looking for thank you or anything like this, but I had daughters at this school, and I see how hard you guys work, and I understand the complaint, but man, some of these is just tedious. Just so you're clear, every problem I assign is intentional. I go through the book, and I look at every problem, and I say that's a waste of your time, but I don't. So when you didn't do number 25 or whatever, that was intentional. That was just because I forgot it. I'm trying to be cognizant of your time, but also, obviously, then that on the flip side means if I assign a problem, it's to me worth it. All right. So, questions? Any questions? You're locked in. I love it. Shout it out if you have any questions on 26. Don't be shy. Okay. All right. Well, I'll just be walking around then. If you have questions and you're shy or you have laryngitis, then wave your hand vigorously and I'll come over to you. Sure. Okay. So that's actually new to use the color.
7, negative 1/2.
So I feel like the only thing that's wrong is when you combine. Stop this recording.